Our title today is Disturbing Equilibrium. At equilibrium, we know that the forward and the reverse reaction rates are equal, and concentrations of reaction components are static. So that is the equilibrium condition, and that is nothing new. And so the question is then, what happens if you make changes to a reaction that has reached equilibrium? And so that's what we're going to talk about today. What about if you change the concentration of either a reactant or product? So you add more product, or you add more reactant, or you remove reactant once the reaction has reached equilibrium. What happens to it? We'll also talk about changes in volume, which basically, if we're talking about gases, is change in pressure. And then finally, what about changing the temperature of a reaction system that has reached equilibrium? Okay, Le Chatelier's principle, it states that when we disturb a system that is already at equilibrium, that has reached equilibrium, that the concentrations of reactants and products shift so as to partially undo the effects of the disturbance. Okay, so part of the problem with talking about Le Chatelier's principle is this idea of shifting concentrations, and shifting in terms of the reaction moving to the right, or shifting so that the reverse reaction rate increases momentarily. So when we talk about shifting, what we're really talking about is either, if we say that the reaction is shifting right, that means that the forward reaction rate is increasing momentarily for the thing to reach equilibrium again. Or if we're saying that the reaction is shifting left, that means that the reverse reaction rate is increasing momentarily to undo the disturbance until the thing reaches equilibrium again. Okay, so the first thing we're going to talk about is changing concentrations. So if a component, and that can either be a reactant or a product, is added to a reaction system at equilibrium, the reaction will shift in a direction that lowers the concentration of whatever it is that you added. If a component is removed, the opposite effect occurs. So let's look at an example. All right. So let's look at the Haber process, which is N2 N2, so nitrogen gas, plus 3 moles of hydrogen gas reacts to give us 2 moles of ammonia. All right, so there we have it. Now, right away I've made a mistake. Right? So it should be now. All right. So let's say we add some hydrogen. Okay, so this thing has reached equilibrium. Forward, reverse reaction rates are equal, and concentrations aren't changing. Okay, we know that there's frantic activity back and forth, but the concentrations the overall ratio of product to reactant is not changing. Okay? And so let's say then we add some hydrogen. So if we add hydrogen gas to this reaction mixture, I better use something really bright so we can see it. If we add hydrogen, which way is it going to shift this reaction momentarily until it reaches equilibrium again? Well, it wants to work to undo that extra hydrogen. So if you add hydrogen, it's going to shift this reaction to the right momentarily until the thing reaches equilibrium again. So if we add hydrogen gas, it will cause this reaction. Add hydrogen causes reaction to shift right. Basically to reduce or to counteract this disturbance of adding it. It wants to get back to equilibrium. So when we say that it's causing the reaction to shift right, that means that momentarily the forward reaction rate is going to increase. It's going to be greater. The forward reaction rate, I shouldn't say that. The forward reaction rate is going to momentarily be greater in relation to the reverse reaction rate. We can't ever do anything to actually change the rate unless we are changing temperature. But momentarily, the forward reaction rate will increase compared to the reverse reaction rate. It will be greater than the reverse reaction rate. It will be out of equilibrium, and we term that as shifting to the right. What about if we add ammonia? If we add ammonia, which way is it going to shift the reaction momentarily? It's going to shift it to the left. What if we remove nitrogen? If we remove nitrogen from this reaction mixture, it wants to counteract that disturbance. And so again, the reverse reaction rate will be greater momentarily than the forward one. And so it's going to shift this thing left to replenish the nitrogen that has been removed. All right. So let's talk about volume. When volume is reduced, now you can see this written a couple of ways. So if you reduce the volume, that is the same thing as if we're talking about gases. If you squeeze down the volume, that means you are going to increase the pressure of that reaction system. So the system is going to respond by decreasing the pressure. And that is moving in a direction that decreases the total number of molecules that are in the reaction mixture. When the volume is increased, that means we are decreasing the pressure, the opposite is going to occur. So let's just go back to our old friend the Haber process, and we're going to use the same thing. So we've got some ammonia. No, we don't. We have no ammonia yet. We will, but we don't yet. Okay, so we've got some nitrogen, and it's going to react with 3 moles of hydrogen. And it's going to give us how many moles of ammonia? 2 moles of ammonia. Okay. Now, this side, the product side, has 2 molecules or 2 moles, depending on the magnitude we want to talk about this thing. So we've got 2 molecules, and this side, reactant side of the equation, has 3 plus 1, which is 4 molecules. more molecules on this side in relation to this side. 4 become 2, okay? All right, so if we increase the pressure, if pressure goes up, this system is going to respond to that disturbance by decreasing its pressure. So if the pressure goes up, the system will respond by decreasing pressure, and that happens by shifting in the direction that has least number of molecules. And which direction has the least number of molecules? That's going to be the right direction, towards the product. So if the pressure goes up, the system responds by decreasing its pressure, right? It's counteracting the disturbance. And in this case, it's going to go on this side, right? It's going to go right. So the reaction shifts right to decrease its pressure, because there's less number of moles of gas or less molecules of gas. Okay, what if it's the opposite direction? What if we decrease the pressure? Okay, if we decrease the pressure, then this system is going to respond by increasing the pressure, right? It's going to counteract it, work the opposite. And to do that, it is going to shift to the left where there is 3 plus 1, 4 molecules or 4 moles of gas, creating greater pressure. All right, last but not least, the worst of all. Scary. It's probably not going to get this right away. You're going to have to read it a couple of times before you get it, in the Princeton Review and in your textbook. Okay, if a reaction is endothermic, so if it's endothermic, that means it has a delta H. That is what? Positive or negative? Positive or negative? Positive. An increase in temperature will shift the reaction to the right. If a reaction is exothermic, delta H is negative. An increase in temperature will shift the reaction to the left. Okay, so let's think about this for a minute. And, of course, vice versa, the opposite is true as well. So, if a reaction is endothermic, that means that as that reaction goes forward in the forward direction, it is absorbing heat from the surroundings, right? It's cooling. It's actually cooling the surroundings. And so if you increase the temperature of the reaction, it wants to, I'm anthropomorphizing it, but it will respond by cooling itself. So if you increase the temperature of an endothermic reaction, it's going to move in the forward direction to cool off, to counteract that heating. And so counteracting the temperature increase means going forward because it's an endothermic reaction. And endothermic reactions absorb heat from the surroundings, cool the surroundings. Okay, if a reaction is exothermic, that means as you go forward, it is going to It's going to generate more temperature, increased temperature, increased temperature. If you increase temperature, it wants to work, or the system, the reaction system, will respond by shifting in a way that will counteract that temperature increase. Now, if it's an exothermic reaction, that means that the forward direction is the heating direction. And if you're increasing the temperature, it's going to respond by going in the cooling direction. What is the cooling direction? The cooling direction is going to be the reverse reaction. So an endothermic reaction, the forward reaction is endothermic, the reverse reaction is exothermic. For an exothermic reaction, the forward reaction is exothermic and the reverse reaction is endothermic. I think the easiest way to approach any Le Chatelier's problem is to think to yourself, okay, what is the change that is occurring? And what can the reaction do to reverse that change? How can it counteract that change? Which direction counteracts that change? If you remove something, in which direction does it go to get that stuff back? If you increase pressure, which way does it go to decrease the pressure? If you increase temperature, which way does it go to cool itself? So always be thinking to yourself, which direction is going to counteract the disturbance?